Hello, everyone. Thank you for joining to this webinar about integration of solar energy in the 5G DHC networks. So as you can understand, today we are going to talk about fifth generation district heating and cooling technologies and also about solar energy. So two main topics. My name is Anna Bronzes. I'm from Open Universiteit. And my colleague Eugenia Bueno Martinez also joined today from Open Universiteit will support to host this webinar. We
Actually, sorry
yeah
to interrupt, Joanna, but I don't have the option to accept people, so you're gonna have to do it yourself.
okay, good.
Sorry.
So yeah, we are partners of Interact D2GREES project and yeah, one of the leaders of 5G DHC Industrial Alliance. So today I would like to share with you our program. So let me skip for the next slide. I hope you can see that. So very interesting list of speakers. So we have today Geert Moermans from Vito, and he's going to present integrating solar energy in thermal energy systems and their effects on investment in solar technology to improve 5G KPIs. Unfortunately, today we got very last moment notice that Hugh Moore cannot join today, so we will skip his part. But we will have Benoit Denis from LLC who will present legal aspects in integration of solar in 5G DHC. Then we have Jonah Michaels from EFTech. So he will give a real life example on the exploitation of 5G DHC networks and the potential of solar. And we have Asa Lacher from Akopa Solar, who is going to present PVT solutions in 5G DHC networks. And the last but not least, if you have time, we will have a small interactive activity and some surprise at the end of our webinar. So on this point, I would like to give floor to Geert Moermans. Yeah, Geert, the floor is yours.
Thank you, Anna. So my presentation will mainly about some results that we had during our research done in the D2Grids project. So my name is Geert Moermans. I work for Vito Energyville. It's a research institute. We're located in Genk in Belgium. And we are doing, it's a joint effort actually, Energyville. It's Vito, it's a research institute. We're joint forces with University of Leuven and Hasselt together with IMEC, and we all focus about studying on energy parts of, we do storage, we do production. So anything related to energy is done within Energyville. So I would like to focus on the integration of solar in 5G DHC. Is it a good idea or not? Let's hope that we all have the same answer by the end of my presentation. Maybe just a summary within the D2Grids project, which was an Interact funded project. We had a lot of partners, and the aim was to roll out the 5G DHC technology in Northwest Europe. We had several pilot sites. We had some following regions. It was a consortium of 18 partners in total, and you can have a look at information on the website that is linked to it. So within this project, we found out that 5G DHC, first, it wasn't really defined. So we came up with a schematic design of what is 5G. It's exchange of energy within a system. So we have an ambient loop, you have customers or production added to it. They all interact with each other. It's an optimizing of exchange energy. It's decentralized, etc. So we aim actually for a new generation of networks where we have low temperature as a key and exchange of energy also as a key. This is what 5G is all about, and we actually summed it up in nice core principles, the ones you may already have seen before. But we aim actually for 5 core principles, which also nicely relates to a 5G network. And the first one is that we like to close the energy loop. So we will focus on exchange of heat and cold between the end users. The second is we want to use low-graded sources for low-graded demand. So we are not focusing on, certainly not on high-graded demand. And if a high-graded source is available, we would only consider it as an extra and not actually look for a high-graded source as the primary source of the whole system. Third principle is about being decentralized. So we only want to deliver the energy when it's needed and where it's needed. So we want to distribute the energy and elevate temperatures or reduce temperatures as close as possible to the end consumers or end users. And we want to integrate actually the approach of energy flows. And this, you can already see that there's a solar pictogram in this indicated. So we want to integrate actually every possible energy flows within our whole system. And then the last one is focusing on local sources. So I would like to give you an overview of where solar can be important and where solar can improve some of these core principles or improve KPIs related to the principles that we have defined within the D2Grids project. First of all, what do we mean by solar? So first of all, I think we all know these PV panels, but when we look at PV panels in a 5G system, we mainly look at PV panels on an individual building, on an individual house, but they can also mean like having an PV installation, like a PV field that is connected to the system, or it can be, yeah, it can be small scale, it can be large scale, whatever. But yeah, then of course we can integrate it in the whole system, which is, I think, well known for everybody in this meeting. The next one of solar that we could use within a 5G system is to integrate solar collectors. So that's actually mainly the same idea as using PV panels, only here the energy from the sun is directly converted into thermal energy and not into electrical energy. So it's actually, we are producing hot water within our system that can be used by local users or can be distributed to other parts of the system. I also would like to indicate, but we have a specialist who will give a presentation later on, but we can also use PVT in this setup of our 5G design, which is actually an integration of the two previous ones. We can use solar panels for production of electrical energy, but also for thermal energy. And when you combine these two, you come to a PVT panel. The next one, more exotic, is using concentrated solar, which is, yeah, kind of a big installation, and it's not always, yeah, you will see in the next examples that it's not always the best solution to integrate it in a 5G DHC system. But I will use these four examples later on in the presentation to give you an idea if they're a good idea or not to integrate them in a design of a 5G DHC. So for the CST, you have several options, but they mainly have the same principle. They use the solar energy with use of mirrors, or can be curved, can be flat, and they all concentrate their solar energy to one point at which you can have like high temperature water production or whatever. So why would we like to have solar in our system? And is this solar then a local source? Because yeah, so the sun is not really a local source. Can we consider it as a local source? We said that we would like to have in a 5G system, we would like to have as much as exchange of energy as possible, but how do we use this solar for exchange of energy? can we store somehow this energy, because that will be needed if we would like to make use of this energy in all its forms. And then, as you could already see by the examples, we have several temperature ranges, like the CST, they produce very high temperatures. We have the PVT panels or the solar collectors, which have more temperatures of a lower range. And then most important is, in a design, will they improve our KPIs that we have set within our project? And how do we take them actually into account? Those are questions that I would like to answer together with you in the next few minutes. So the first set of KPIs that we've defined are linked to closing the energy loop. So we focus on the percentage of we focus on actually exchange of energy. So how much energy is bought in from external sources and how much of this energy is internally exchanged. These are two parameters that we would like to look at for indicating KPIs linked to closing the energy loop. So in the right corner, I already placed PV, PVT, the solar, the concentrated solar, and then the solar collector. You can see that I've indicated concentrated solar thermal as orange. The other three options, I think, are good options to improve these KPIs, as for example, by production of electricity via PV, or production of thermal energy via solar collectors. You can reduce the amount of external sources, so that will improve your KPIs. A CST, on the other hand, it's concentrated solar, it's high temperature. I'm not sure that it's an added value and integrated it in a system, so that's why it's in orange. It might be a good idea, but we have to look at it case by case. So looking at the KPIs, the first one, internal energy exchange, I think we cannot say much about exchange of energy improved by solar technology, as it is mainly production, and it has to be linked to other technologies for being able to exchange energy. So on the next one, we said we would like to have KPIs also for using low-graded sources for low-graded demand. So we look at actually where do these energy sources come from. We set a temperature limit of 50 degrees. There's still a discussion, I think, about if we have production of electricity via PV, is it low graded, is it high graded? Mainly, the electricity bought in from the grid is considered as a high graded source. So that's why it might improve by using PV, PVT, or the solar collectors. CST, on the other hand, is clearly a high graded source, so that will not improve the KPIs that we've set in the 5G system. We would like our system to be decentralized and demand-driven. So there too, we've set some KPIs. So we want to reduce the thermal losses within our ambient loop, and we want to have as much as possible active substations close to the end users. It's not directly linked, but of course the PV, PVT, and other solutions, they are local, they are decentralized, they're mainly on building level. So they probably can have some influence. It's not clear. That's why I've put them in orange again. CST, however, is a centralized solution mainly, and they will not improve the KPIs of being decentralized or demand-driven. So what we basically need to improve is we need storage. So if this electricity or thermal energy is produced on building level, and we want it to be decentralized and demand driven, we need storage to optimize this. So as a solution alone, it's not beneficial, but in combination with storage, it will certainly, it can improve the KPIs. When we look at integration of energy flows, I think that's the most clear one. If we have other energy flows from electricity, from other sources like this concentrated solar, we will certainly be able to reduce peaks within our system, and we will hopefully can reduce the total capacity which is needed for heating and cooling, as we have this as an auxiliary system, let's say, of our energy production. This too needs to be combined, I think, with storage, and it is mainly focusing on heating. So for cooling, we have the conversion still of electricity to cooling via dry coolers or other systems that are installed. Local sources, I think that's clear. If we have PV installed, PVT, solar collectors, or CST, they're all local sources, so they will clearly contribute to improving the KPIs of being local, of having local sources. So as a summary, maybe, if we use solar and 5G DHC, solar, the electrical part, I think it's clear that there's a need for storage as well, combined to it, storage in some form. The most obvious one is battery storage, but there can be other forms as well. It can be conversion to another to another energy component. So there might be several solutions. We can clearly do peak reduction of the electricity demand by using this local produced electricity. So we will actually not generate big peak demands from the grid, at least not as big as they used to be before the installation of electrical solar PV panels. So we will reduce the electricity from the grid. In some of the examples that we have studied, we could see that you could also use, if there's an excess of electricity production, you could use this for balancing your geothermal, so for generating extra cooling. But this will influence the first principle, as you will not close the energy loop, probably, as it's mainly done by dry coolers. So you will generate actually an open loop system. So there are some pros and cons to do this. And then, cooling, if you really have a large cooling demand, you need electricity for the conversion, as there's no direct production of cooling via the sun, of course. Solar, the thermal component, it's mainly heating. It's actually only heating, and that's done by thermal, or you need conversion. There's a need for storage there as well. I think in a combination, for if you produce thermal energy, you can also reduce electricity demands, for example, of heat pumps. If you already produce hot water, you don't need to switch on the heat pumps, maybe not altogether or not at full capacity. Then you can also reduce the electricity from the grid. And I think the main component for installing solar thermal, like the solar collector, for example, is for creating domestic hot water, as it is mainly on a higher level than it is distributed via the network. So this can be a component of, within the system that can be very beneficial. So I think in an overall, I think integration of solar, just on a technical part, not the financial part, but installing solar can improve almost all KPIs of our system. So focusing on the first question, that is it a good idea to install solar? I certainly think from a technical point of view that it's a very good idea to install solar, but of course there's an economical part to it as well. And I think this can be, this must be studied case by case if it's also worth the investment, let's see. So for any further questions, you can contact me later on this email address. And for now, I think I will give back the floor to Anna.
Yeah, thank you, Geert. It was really interesting presentation about KPIs and introducing solar in 5G DHT systems, and really this question about if the solar improves the KPIs. I think we almost convinced about that. And let's hear other presentations of our speakers, and we can make some draw-up conclusions at the end. If someone has questions to about this presentation or questions to hear, you can post it in the chat or leave it at the end so we can answer at the end of the webinar. But now I would like to give floor to Benoit Diniz, and he will present legal aspects of integration solar in 5G DHT network. Benoit.
Thank you, Anna. Hi, everybody. Thanks, Geert, for your presentation. So I'm Benoit Diniz. I'm a lawyer. I work in the French law firm based in Paris, which is called LLC and Associés. I currently head the affairs in the energy, the business and energy department within our law firm. And we, as a law firm, we've been involved in the D2 Grids project for basically two main aspects. The first one was to determine some kind of a pricing model that would be applied to 5G DHCs. And another one was accompanying some of the pilots, and especially the French pilot in Paris-Saclay, in setting up actually its coupling of PV solar to the grid, and how to do so. And we've also accompanied the district heating system operator in doing so. So our presentation today will mainly focus not on if it's a good idea to do it, and thanks, Geert, for confirming it is, but rather on how to, on a legal and more or less economic level, both being all the time very closely intertwined. So here we go. We'll share my screen. So the first thing to take into account when you think about integrating PV solar is who produces electricity. And I will mainly focus on PV solar because there lies the difficulty, which is combining two networks, the electricity network and the thermal network. And especially within the electricity network, it's especially hard because the technical constraints are such that the regulatory framework around the production of electricity is always very, very complex, with balancing parties, with producers, consumers, and as you know, also distribution system operators. And the combination of all these people gives you a very complex framework. So the first thing we need to think when setting up all the PV solar coupling with the 5G DHC is how is the state of our network. So here we have three different ways of organizing a network, which there is no better way than one way than the other. It's just separate ways of you could encounter in real life. We will talk about centralized and decentralized energy production. But the difference you need to understand with what Geert presented before is that we are not talking about production assets when we talk about centralization or decentralization. We're not saying that a a network is decentralized because you have production assets, PV plants all around the network. Here we talk about centralization or decentralization of the production ownership, which is who produces and not where it's produced. So when you have a centralized energy production system, you would have one sole energy producer, which would generally be the network operator. That's, for instance, for the time being, the case in the pilot in Paris-Saclay, where we have a geothermal energy and biomass, gas heaters that are operated by the same company. And what is foreseen is that the same company will afterwards, in several points of the network, install heat pumps, which will be coupled with solar energy. But still, we consider it centralized because one sole person doing the energy production. We have another model where the only thing centralized is the thermal energy production. So that will be the case of the pilot in Saclay, but in a second phase afterwards, where the local urban authority will foster a plan to promote people's production of solar electricity, and then the energy producer will acquire this electricity to power the heat pumps and then power the district heating and cooling system. And then we have a fully decentralized energy production, and then you can have any kind of setup where you would have several people, different people producing energy and different people producing heat, everybody at home or whatever. So we have this fully decentralized model as well. So first, we need to have this idea of who produces what and in what circumstances. And then once you have all these ideas of who produces what, you can play with your 5G DHC system, because you can, for instance, here in the figure you have on your screen, you can have, for instance, some dwelling somewhere over the network who produces electricity, can give it away to the heat producer, which is another dwelling, another part of the network, because this dwelling needs heat at that point in T1, and then in T2 maybe you cannot produce solar energy, but still the solar producer, who is also a dwelling, needs heat for his own benefit. And then you can also have mechanisms where you exchange solar power in the first period in exchange for heat in the second period. So that's the fact that you can couple both technologies gives you a lot of flexibility to the system, even though you only rely, for instance, on financial mechanisms and not only on thermal storage. You cannot couple solar power to 5G DHC systems the same way in other countries because of the regulations. The most common way to commercialize for one PV producer to provide electricity to a heat producer, you will find it pretty much all over Europe, except if I'm not mistaken, in France and in the French part of Belgium. You can install your PV power plant anywhere on a private grid and then sell your electricity to, I don't know, the owner of the house. And that's the basic framework, and that's the most efficient framework. But unfortunately, that's not the case we see in France. You can also have another framework which is allowed in France, where you are the same person who produces solar power also produces the heat. Basically, that would be the house owner having his own solar panels. But that means he needs to operate it by himself. And then you have a third scheme, which is available pretty much everywhere over Europe, which is you can connect your solar power plant to the public grid and then send your electricity to the heat producer. But all these schemes, you cannot have them. I mean, it's not that simple always, and you have some constraints. What you have here in France is the only way that someone can produce solar power to his own benefit and to power the heat pump. You need to be the operator of the solar plant. The only flexibility you get is that you don't need to be the owner of the solar plant, but still you need to be declared as a solar power producer if you want to be able to consume your own energy. Second scheme that we have is what we call a collective consumption scheme. Under this scheme, you basically have a basic operation where you have a power producer who injects the electricity within the power grid, the public power grid, and sells it to some specific customers. It's pretty efficient now. It's been hard to develop the whole scheme, but now it's pretty efficient. But there are a lot of tax disincentives to this solution that make it less attractive than the first one that we saw before, which is the individual self-consumption scheme. There are lots for the collective self-consumption scheme. There are lots of constraints. You need to sell to somebody who is within a 2-kilometer perimeter. You cannot have too big power plants. It's electricity only. But the good thing is the way the electricity is dispatched to the withdrawal delivery points. This is all done by the distribution system operator, which is very less expensive that you would have in power purchase agreements. We have one last way of distributing energy and commercializing energy, and this last way is through power purchases agreements. What we know as power purchase agreement pretty much everywhere in Europe, which is a direct agreement between a producer and the consumer. By itself, it's not that difficult. I mean, you have a producer, you sell all your electrons to consumer, and your consumer is the heat producer, uses it for his heat pumps, and that's basically simple. The problem is that where you have a 5G DHC network and decentralized production and decentralized consumption, you may need one production asset may be able to dispatch the energy to several consumers. That would be the most efficient way of maximizing renewable energy use within the network. And there lies the big difficulty, because you need to find some way to allocate the production shares, which is kind of difficult when you first have when you have several consumers, because you need to have some way of determining how you share it. But it's not the only difficulty when you also have several power producers, because if everything is injected within the power grid, then only the balancing entity is capable of knowing who produced what and who consumed what. So the balancing entity is the only person here who is capable of telling the hospital that it needs to pay whatever euros to the town hall who's producer, or to the dwellings who are producers, and so on and so on. So organization-wise, that's kind of difficult. So we have several solutions to counteract this legal difficulty. The first one is, well, centralizing thermal energy production so that you don't have 3 people here, but only one district operator who produces. That may be sub-efficient in terms of decentralization, because maybe your district system operator cannot put heat pumps in every building and have a fully decentralized system. You can also resort to intermediated PPAs. What would that mean? Basically, every producer here sells the electricity to one electricity supplier, and the electricity supplier sells this electricity to all these consumers. But you have a loss of economic efficiency, because your energy supplier will take a margin on the sales of electricity, but also there's a question of the traceability of the energy, because if it's the energy supplier who provides this energy, nothing guarantees that the power plant that was installed on the town hall is actually feeding the hospital. If you have this direct agreement, I mean, there is still it's still questionable, because bottom line, all the electricity is just injected into the grid. But still, you have the balancing entity that can make the match between the date and time where the electricity was produced and the date and time where the electricity was consumed. And physically wise, if both are not that apart one from the other, it's highly possible that it's actually the same electron that is consumed here that was produced here. The last solution would be to multiply bilateral PPAs, which would mean the town hall enters into one PPA with the hospital, with the dwelling, with the cars, and so on. But that would be an extremely tedious exercise, and that we would really not want to incentivize these kind of solutions. We need also to consider taxes, which are very, very important key of energy, solar energy projects and its coupling with the 5G DACs, because usually taxes are capable of making a business case or not. In France, and you will see the same kind of tax regulations pretty much everywhere else. You will almost all the time have an excise duty, which is a tax that is imposed on consumption. In France, it ranges from 22.5 euros per megawatt hour to 32 euros per megawatt hour, depending on the power that you request. Before the events in Ukraine, excise duty amounted to about 1/4 to 1/3 of electricity invoices every month. So this is really important. Then you have grid access fees. These are fees that are used for public grids. And then production tax, land tax, VAT that we may all know. The way you can find tax exemptions will be crucial to setting up your coupling. For instance, here you have a French setup where you would have here if individual self-consumption, and the electricity produced here and consumed here by the same person on the same site is for sure exempted from excise taxes. That gives you pretty much a 25% bonus on your production cost. You have another situation where you have the same heat producer who produces heat, but on somewhere on the grid. And there is some loophole for applying for the excise duty exemption. But one thing is for sure that you use the public grid, so you have to pay the grid access fees. And there you have, if someone else is here, is now not the heat producer, not the solar producer, well, you pay the full amount. And that is pretty much the same for the consumer here. And you also have here just this situation where in France, if you have this guy producing solar energy here and selling it to this dwelling, heating his house with a heat pump, well, that would be totally illegal. So that's there is a real business case to limit your setups to these two options here. All these amounts to some organization of your operation. We are talking about here about energy projects, and when you think of energy projects, you will always have these five items in mind. The first one is grid connection. You will need to have relationship with the DSO, because whatever the setup, you always need to connect your plant to the public grid, or at least in France that's the case. You cannot be fully off grid or without declaring your power plant being off-grid and somehow connected to it. You have construction and maintenance, obviously, except if you are capable of doing it by yourself, but that's almost never the case. Energy commercialization, which we already saw a bit before. Land securing, which is you need to put your solar panels somewhere, and so you need to be sure that you can put them there, that you have the right to put them there. That makes sense. I mean, it's straightforward when you're the owner of the building where you put your solar panels. But when you think about 5G GAC systems, you will have public buildings, you will have commerces, you have a lot of different situations. So you need to really focus on land securing. And the last one is the energy investment, which is really proper to any project finance project. In terms of land securing, what you will seek are long-term leases, because you need, if you dismantle a solar power plant, the value of the power plant drops so much that once it is in place, you really need to make sure that it stays in place until the plant is dead. So you need long-term lease for over 20 to 30 years minimum. What you also need are in-rem rights. So it's a special kind of rights when you make leases, where the rights you have follow the building and does not follow the owner of the building, which means that if the owner sells the building, you can keep on staying on the building. If you don't have these in-rem rights, if the owner sells the building, the next owner may kick you out of it, and then you will be in big trouble. The second one, with respect to construction and maintenance, you have the EPC contracts for engineering, procurement, and construction contract. Make sure you have a performance guarantee in these contracts. What we see is about 95% of performance, which is unlikely to be accepted in operation and maintenance contracts. Completion bonds. So you have usually a retainer of about 5% to make sure that the solar power plant is fully completed. And then you have the operation and maintenance contract with an availability guarantee. You need to have your power plant available about 98% of the time. Loan agreements and securities, that basic project finance, that's not really necessary to develop here. It's not really the case. In terms of grid connection, you have all these contracts you need to enter into with the DSO in France. The old deeds of incorporation and the CSC agreement, collective self-consumption scheme agreements, are those very specific agreements for self-consumption schemes. And last but not least, you have the energy commercialization agreements. Beginning with the PPAs, usually we see a take-or-pay clause, which is you as a consumer, you need to buy all the electricity that is produced by the energy producer, the solar energy producer. That is when you're the sole consumer, obviously. Default payment guarantees and penalties and bonuses, which are basically based on what the market will offer you otherwise, what you would need to pay if you as a consumer, if the plant doesn't give you the electricity that you requested. So this is the end of our presentation. I will try to make a quick overview on how to set up your solar plant coupling with the 5G GAC. We're available. I think I have normally. I thought I had put my email address, but I will put it in the presentation that we will forward to you. Thank you very much.
Thank you, Benoit. Thank you for presenting the legal aspects of integration solar in 5G DHC networks. I think it was really interesting to see that we can have some challenges, but there are also solutions to overcome these challenges, and especially was interesting to see how to pay less taxes. I think this part is really attracting everyone.
There's a real business case to it.
Yeah. Yeah, and as far as I know, you also developed smart contracts for D2GRID's project for our pilots, right?
Yes, indeed. We studied in cooperation with CRINFlex the way to do smart contracts. So there is a caveat before going further on, that smart contracts are heavily relying on sorry, it's not the timing. Well, it's heavily relying on a huge important amount of energy. Sorry, I don't have the word that slips my mind. Blockchain, sorry. It's heavily relying on blockchain, and blockchain has a very, very intensive use of energy. So you would really need to focus it on you need a critical mass of your 5G JDC before setting it up. But we've worked on establishing all the conditions that you would need to code in order to be able to design your smart contracts and exchange electricity against thermal energy.
Sounds very interesting. So if anyone has questions to Benoit, please keep it till the end. You can also post it in the chat. But we are going to move to our next speaker, Jonah. You're going to present a real-life experience of integrating solar in 5G systems, right? So floor is yours.
Yes. Everyone can see my screen. So I'm Jonah Michiels. I'm business development manager with IFTech, and I'm going to present some of our use cases where we already have implemented a 5th generation district heating network and are in the process of examining and experimenting what all the potentials of solar integration can be. So what we do is shallow geothermal energy storage. So when we talk about geothermal storage, we don't go deeper than 250 meters. Most people will think in geothermal going way deeper, higher temperatures. But what we will do is basically create a underground thermal battery storage for heat and cooling, where we would capture the heating in summer and use it in the winter to heat with summer heat, using the thermal battery storage and a heat pump where we have very high yields of COPs. Whereas in the summer, we would do the opposite. We would use the winter cool for cooling in the summer, with even higher COPs that we can achieve. So what we basically do is we connect the usage of heat and cool via a geothermal battery in the underground. Now, the technology that we would use and that we have the most in-depth knowledge about is ATS. This is an open system where you would use an aquifer below the ground, where you would pump the water and thus creating a cold and a warm bubble under the ground, which is protected in this aquifer. You can see the potential here on the Flemish region, because that's where we have the most projects, where you can see, for instance, that it's not an easy fit. It's very dependent on the geothermal conditions. So where in the east of the country, you would have a big potential for open systems. It's not so much the case if you go more to the west. But you can also use a BTS, which is a closed system where you would basically have a heat exchanger in the underground, so we won't be pumping any underground water. And here you can see the same map of Flanders, but this time the potential for the thermal conductivity in the underground. So this technology you can use almost everywhere. It's more universal. but especially for bigger projects, it's more expensive, and you have less efficient yields of COP on the technical side. Small word, so is IFTech still a young company, 20 years now of primarily national but also international experience in the Netherlands and the UK. Clear mission and a young, driven and dynamic team that is very eager to reduce a lot of carbon dioxide emissions in new building projects. I have with me two use cases that are, this one's already finished, the other one is in development, where we have installed a 5th generation district heating network. First one is in Hasselt, which is very much to the east of Flanders, where we have 25,000 square meters of retail and a bit more than 400 dwellings, all apartments. Everything is, from an economical side, organized in an ESCO, in an energy service company. So what we would do is we financed the groundwater system and the distribution, and going in the buildings, that's where the end of our assets are. So the heat pumps in this case are not a part of the ESCO. So we only provide the heat pumps with the necessary temperatures that they need for the high yields, but we don't have them in operation. In this case, this results just this technical design with an ATS system in an annual saving of about 750 tons of CO2 annually. This is compared to gas, because that was still an option when this project was developed, and a return on investment financially of 11 years, doing 6 boreholes in the chalk, and have a heating and cooling capacity of about 2 megawatts. Now, the system that we use here, simply because we have multiple users, retail and dwellings, so apartments, we have different usage of different needs of heating and cooling. So we would use a 3-pipe system where we would supply a semi-constant temperature of about 15 to 20 degrees, where all the users, they would use that and they would make heating. And they will then, when they make heating, so in the case of the dwellings, they will also produce cold cooling, which then gets collected. But the opposite happens with primarily the retail that uses a lot of cooling. When they make cooling, they produce heat. So especially in the autumn and in spring, the whole system in itself is already in balance. We see, for instance, that the retail starts already in February, which is still a very cold month in Belgium. They already start cooling. And so there are multiple days in the year where the usage on the district heating network of the demand of heat and cooling is about the same energetically. And so we won't be using the groundwater system at that time. Of course, in summer and in winter, you'll have a dominant demand for heating or cooling. And then we would use, of course, the groundwater system, the ATS system, to balance the neutral net. We already have a project in Brussels. It's not presented here in this presentation, but there we supplied only retail, and we used a 2-pipe system, which you couldn't use if it's it's only a one type of client that you use. So since it's only retail, we could save costs on the capex by installing a 2-pipe system and not a 3-pipe system. Now, the biggest thing that we learned, or the biggest advantage of this type of system, is that it's a very low temperature, so you can combine heating and cooling demand very easily from the same distribution channels, and you can save a lot on capex as well, since the distribution can be completed in PE, where in higher temperatures distribution networks you would still use steel, and you would need to insulate the distribution channels as well. Whereas we would, if we install a neutral net in the ground, you don't really need to insulate it, simply because you have very, very low heat losses, simply because the difference in temperature between the piping and the underground is almost zero. Now, if it comes to this case, we don't use PVT, so we do need a balancing system, since the demand for heat and cool is energetically not imbalanced in this project. But we use here surface water. That's simply because the project is located next to surface water, which is a very easy and a cheap way, or cheaper way, to restore balance. And you can use this source either in winter to charge cooling, or in summer to charge heating, to balance out the entire system. PV here, since the real assets that use a lot of energy, meaning the heat pumps, since they are not part of the ESCO, we don't have a big installation of PV. This is limited to 150 kilowatt peak, which could be a lot more if the heat pumps were also assets of the ESCO. We are, however, still looking at an EMS implementation to have a better prediction of the yield of PV, and to then optimize our water consumption. Another project is Hertogensitte. It's in Leuven, which is a more difficult underground for ATS system. The very first phase we did ATS combined with surface water, but all the other phases will be BTS, because it was proven technically not feasible, or too expensive to keep on using ATS. But this program is about 10,000 square meters of retail and 465 dwellings. Whereas on the geothermal sound, we would use 288 boreholes for a 2 megawatt heat and 1 megawatt cool capacity. And this would also reduce the annual CO2 emissions with about 1,000 ton annually. Here, it's also provided with an ESCO, so we provide heating and cooling as a service. So there are buildings with collective heat pump systems, where we would supply central heating temperatures, but everyone still has their individual booster pump for domestic hot water. So that's something that we do not provide in this ESCO. Once again, if we look at the integration of solar, PVT, same issue here. I see that there's a small error in the presentation, where here we also use surface water, so you could also use more active cooling if for instance, your primary demand is heating, or in most projects where we don't have surface water available, we would use air source heat pumps to balance out the demand between heating and cooling. When we look at PV, since the project is still in development, we're still looking at that. Here we have more a lucrative business model and more added value where since the heat pumps are, the centralized heat pumps are a part of the ESCO, we could use this higher thermal storage potential to produce an excess of heat. For instance, when there is an excess of PV, or where we would make active cooling when there is an excess of PV, but that's still to be determined. And of course, what we see in these kind of projects, especially the combination with the charging of electric vehicles, is a nice added bonus to the business model of an ESCO, where you can provide an extra service. And of course, if you have PV and you can provide a smart charging, then of course, if there are charging points at the moment that you have PV available, that's of course a very lucrative business model. And of course, here we're also looking at this EMS integration with a combination of dynamic energy tariffs, either by the availability of PV on site or just the actual hour-on-hour tariffs of electricity, where we simply could change the hour on which we would produce heating or cooling, depending on the tariffs that are active on the grid. So that was it from my part. Thank you very much.
Thank you, John. I was really pleased to see all these examples not coming from D2Grid's project, so not the pilot site that we have. Like, as you know, we have 5 pilot sites, but it's really like interesting to hear that someone else is developing 5G DHC network with solar integration. And thank you for presenting these examples. And by the way, my compliments for animations that you presented at the beginning. They look really nice.
All right.
Okay. So we will move to our last speaker, Asa. So you're going to present PVT solutions for 5G DHC networks. So floor is yours. We cannot hear you, so
Yeah. Now?
Yeah,
Perfect. So I'm trying to. Can you see the presentation now?
not yet.
Let's see. Maybe I need to make a small adjustment. Here, just a second. I changed the web browser so it would work better.
It's not yet sharing.
Yes, I understand that. Sorry for that. I'm trying to make it happen now.
Okay, loading something.
Good.
Yeah, we can see, yeah, PowerPoint slides.
Perfect. And it's not showing only the presentation, I see. So, okay. Well, my name is Åsa Lager. I represent Copa Solar from Stockholm in Sweden. We are producers of PVTs and also do retrofits on existing solar parks, converting PV panels into PVTs. I'm responsible for documentation and calculations at Copa Solar, and we have a factory in Germany. Our customers are mainly in Sweden, Denmark, and Germany. At this meeting, at this webinar, I also have my colleague Andreas Pettersson, and we will both be able to answer questions later on. So we are all talking about what we in EU can do to meet the demands of the sorry, I'm I'm changing my slides and you are not seeing my changes. So I need to leave my slide. Maybe Anna, you can take over here and show the slides from your side.
It's changing now. I can see now renewable energy sources. It's
Okay,
called.
so we will accept that it's showing the frame as well. In order to meet the demands for Fit for 55, we need to meet the new demands, 42.5% of the RES renewable energy sources. The possibility to use more of the solar irradiance is existing instead of just producing the electrical energy from the PV panels. We, with the help of PVT panels, can produce much more energy. So the solution with our PVT panel is, if you see on the right, we have an absorber fitted on the backside of a PV panel. And instead of having only the installed electrical power of 420 watt peak, you can add onto that 2,700 watt peak thermal power as well. So, for example, if you would install a PV park with 371 panels, but with the absorber on the backside, you would actually have a thermal energy source of 1 megawatt peak. So this solution is very suitable for the 5G DHC grid, and it would be the boost that you need to stabilize the whole grid. What would the advantages be when you do this kind of retrofit or the new installment with PVTs? So you would still produce low temperature energy from a renewable energy source. The system is optimized for ground source heat pumps and therefore also for the 5G HC grid. It provides a thermal balancing for the system load, and it also supports the TES installations that you would have within the grid, especially during high load periods. So if there is a winter time and there's a high need of thermal heat, then you would actually reduce the amount stored in your storage, and you can revitalize the whole TES system with the help of the PVTs. It would also, of course, always support the daily usage within the grid. It enables also the expansion of the grid. For example, if you want to build new housing, but also if you are expanding your factory, or the need of energy is higher, then you can add more PVTs into the system instead of installing new TES. And also you can replace existing energy centrals, for example, different kind of heat sources like renewable bioenergy or pellets or different kind of energy sources with the PVTs instead. Therefore, also you would be less dependent on the energy prices. So if you look on the right side, this is a cutout of a bigger system view. The two different types that we would work with regularly would be either the bigger PVT parks or the smaller parks, which we call the thermal lifting stations. So with a bigger park, you can stabilize the grid. You would produce the RES and also recharge the thermal storage. You would produce thermal energy for direct consumption, and any excess energy can be stored within the TES. a PVT system can cool down the warm or the cold side as well if there is an excess within the grid. Thermal lifting stations would be smaller parts, about 500 kilowatt peak, and with this help you can lift and stabilize the energy amount within the system. And you can also use it to lower the energy if needed. So this would be a bigger view of how a system could look. We would have housings. We would, in this case, have a hospital as an example. So a hospital would need the cold and would therefore produce the heat from the heat pumps. On the bottom, you would see an example of a factory where you would have, for example, waste heat that can be sent back to the grid. Different types of sources and TS would be needed depending on where you are situated. Like in Sweden, we have a lot of BTS, but within Europe, there are many different solutions. So the electricity that is produced from the PVT parks are also adding onto the grid the energy mix within the grid, and therefore you can use it to stabilize the system, but also you can mount it on commercial and private housings for as retrofits. Both Andreas and I would gladly answer any questions later on. Anna, you decide when, and we also are at the moment planning for about 6 installations with at least 5 megawatt thermal power within Denmark and Sweden. So that's what we are working with at the moment. Thank you very much.
Thank you, Asa. It's really not common to see integration of PVT in 5G THC networks. At least, yeah, as far as I know, none of our pilot sites in D2Grids project has installed PVT. So yeah, thank you for introducing this solution. I think it could be really interesting for some of 5G THC Industrial Alliance members. And talking about questions to our speakers. So I think this is a perfect time if you have questions. So please post it in the chat, or you can also unmute yourself and ask questions to our speakers. Until I haven't gone to the last point of some announcement. So please do that so we can have some time for questions. Okay. I see we have 24 participants today joined, so I hope, it was interesting for you to hear these presentations from our speakers. And please, if you have questions.
If I can ask one to Åsa.
Yeah,
that's okay.
Sure.
Great. So when you integrate these PVT solutions, what I understood from your last slide is that you are basically taking in the return from the network and heating it back to the network temperature and feeding into the system. So, and I presume that the delta T is usually quite low in this 5G network, which is more or less dependent on the delta T that you get across the heat pump simply. So do you face like high pump power consumption, or is it a possibility that you can increase the temperature out of PVT collectors more than the network temperature and then raise the network temperature itself? I mean, what's the strategy there?
So I will actually ask my colleague Andreas to.
Hi, Andreas here. Do you guys hear me? Let's see if my microphone is on.
Yeah.
Okay, good. Well, yes, you're absolutely right that we can both take it from the cold side and we can raise it up to the standard temperature, but we can also run it through the PVTs to we call it stabilize, because we know that the heat pump guys, they don't want to have too much energy into the pumps. But we lowered the you can run at a higher COP with SCOP for a lower electrical consumption, but you get a higher thermal output from the system, and therefore it's also a better investment than putting your money into a storage just to hope that you actually have the amount of energy that you need when you need it. So I think that there are two parts in this that you have to calculate for, but I hope that's a good answer for you.
Yes, thank you.
Thank you. Okay. Just there was a question in the chat to share presentations afterwards, so I can just make sure that we can share a video recording afterwards. So maybe it would be more even interesting for you. Yeah, Benoit, you have a question.
Yeah, I take benefit of it. Yeah, I have a question both for Jonah and Asa. In terms of how long do you have your return on investment? How long do you actually get over the amount you invested and have benefits from what you invested?
Okay, Andreas here again. Well, okay, you're not gonna like this answer. It depends. But if we see that this is a calculated new installation, you would have for 1 megawatt with the like in Denmark, we have a return of invest that are from 7 to 10 years, and that is we still think that is high, because we see that if we do this as a retrofit case towards a case where like here in Sweden we have lots of BTs. We also do in Denmark we have the piling version. The problem here is that people put in larger heat pumps and they really exhaust the ground, and we in here in Sweden it's a famous problem that we have like -10 to -20 degrees in the holes. So this means that your investment there is kind of grind to a halt. So when we do this retrofit on a larger installation, or we install a PVT park towards an existing system where they already have some issues, because that is where we do the most benefit, then we have a return of invest from 3 to 5 years. And then I must also say that we know that there has been an opinion floating around, since we know that our co-colleagues within the same business, I would say, tend to go quite high in the prices, and we're trying to do a lot with this to make this work in a more not the standard PV way where you pay a lot for each watt. So we're trying to change that trend also. Because people need to have a resilient system with good redundancy, as your legal aspect was quite interesting for us, since we see that here in Sweden we don't have any taxes for the thermal when you use it within your own system. But we do also have an exclusion where the battery is very popular for setting in within your own system. So let's say that if we implement the small 5G GHC like Kensa does in England, they have a splendid system with smaller BTs or different kind of TSs together with smaller heat pumps at each residential that they own. And that also means that we can put the PV on top of the PVT, we can put on top of the on the housing, and we bypass the heat pump with the with our thermal connection, put that one straight on the 5G GHC grid, but we can also support and put in a battery before the meter that you can strengthen up and help on the economy at each residential apartment or those. That means that that person owns the battery. And that is a version that we have been looking at to apply here in Sweden also, but here in Sweden it's we're looking at larger installations with in another way. But I think that the Kensa way with the 5 GGHC and the small heat pumps is a very, very good solution that we like to look at and see help to piggyback towards other customers also. Is that a good answer for you? Sorry, it was a long answer.
No. Thank you very much. It's really interesting, and I'm maybe interested also to hear Joanna on about the same results. And
yeah,
thank you very much.
If it comes to the return on investment on an ATS system, it also kind of depends. It kind of depends on how big the project is, how feasible is the underground. But generally, we come to a return on investment of about 7 years as well. So everything, like almost everywhere, it's below 10. It does depend on, because you primarily have your return on cooling, because there is literally no cheaper way to make cooling than in an ATS system. And in that way, if you have a big demand for cooling, which is actually the case in the majority of newly built buildings, then it gets feasible. We do have problems with this technology if it is a district heating network in an existing infrastructure where the majority of buildings are not well insulated and you have a dominant heating demand. But that's just a general problem with a 5th generation district heating network and bad insulation. That's not really a match. And also to say that if it comes to bigger neighborhoods, we do the exploitation in an ESCO as well, then we won't be talking about a return on investment, but an internal rate of return. But that's also, especially in newly built or newly developed areas, it's feasible, and we always find investors to collaborate. I think the biggest issue, if we want to tackle the 2050 targets, is what to do with all these existing buildings.
Yeah, I must say that this way of being able to cooperate in different timelines, if it is going to be built, or if like for us, we have a great strength in a previously built. If you already have a 5 GGHC system with an already installed, like an ATs, that you already everything is dimensioned to that amount of users, but you wanna expand, extend, and all that kind of stuff, then it's easier and or more like this. It's very easy for us to piggyback into this network, put the piping down, and set up a lifting station where you push in the energy that is needed, and then you also can ease up on the system, but you don't have to invest so much in a whole new system, but you can actually expand this in a modularized way.
Okay. Benoit, I think you received an answer. Yeah.
Yeah, thank you very much. That was very interesting, and from my standpoint, the time range you expressed is very but is much lower than what I was actually expecting, and in what I actually see in photovoltaic projects, which are more about 12 to 15 years. So that's really interesting to see that you get to have a much shorter term period of return on your investment. So that's very interesting. Thank you very much, both of you, all of you.
Okay, thank you. I received notification that we have less than 5 minutes left for our meeting. I would like to ask if our participants have questions, just post it in the chat, and if we don't have time to answer now, you will definitely receive answer from our speakers. But I would like to make an announcement, maybe for all our Industrial Alliance members. It will be very interesting. And for those participants who are not in Industrial Alliance, but you would like to join, so yeah, please register, and this activity is also maybe very interesting for you. So we would like to announce about what is coming next and what we would like to do in this Industrial Alliance. So it's not only that we are organizing these webinars and we are just talking, presenting, but there is not really interaction going on. So we were thinking how to support and to organize targeted networking event for you. So you are really, if looking for someone to be connected to, or you would like to have some questions to dedicated person. So we would like to help in this item. So we created this idea about speed date. It's not about love, it's all about business. So with 5GDC Industrial Alliance members. So what is coming next? My colleague will post a link in the chat. This is a short survey. We will ask a couple of questions like with whom would you like to be connected? You can have several answers. Maybe you're looking for connections in industries, maybe in academia, maybe with some policymakers. And you can give us example, a person or a company name. And we would like to organize a short, maybe 15-20 minutes speed date coming like later in November and December, where you will be invited to specific targeted group that you indicated in this survey. So this way, you will get a chance to talk to the interested person, but also ask your question and maybe also to do some business. Okay. So, Evgenia, I hope you had a chance to post the link. Yeah.
Yeah, it's in the chat.
Okay, great.
Sure.
So just take a time. So this link is present here in this chat, but we will also put it in LinkedIn afterwards if you will have time. Just fill it in, and then you will receive invitation for this speed date with 5GDC Industrial Alliance members, but maybe also external people. Okay, so this was the last point from my side. I hope you enjoyed this session, and you will also would like to join our next sessions. And I would like to wish you a good day and see you soon. Yeah.
Thank you. Goodbye.
Thank you for all
Thank you.
speakers.
Bye.
Yep. Bye-bye.
Thank you.
Bye-bye.